In 1990, General Electric risked $1.5 billion and its entire reputation on a radical gamble to build the world's largest, most powerful jet engine, the GE90, for a plane that didn't yet exist. The official story celebrates it as aviation's greatest triumph. But beneath the legend lies a series of audacious bets, near calamities, and innovations that shaped everything flying today. Why did GE wager everything, and what did it nearly lose along the way? Jack Welch, GE's legendary CEO, signed off on a $1.5 billion budget for the GE90, a sum that dwarfed any project in the company's history. The decision was clear. If the engine failed, GE's entire commercial jet business could collapse. Unlike every previous GE engine, the GE90 wouldn't borrow from military designs. This was a commercial-first approach, a clean break from the company's comfort zone. The risk wasn't just financial. Betting everything on the Boeing 777 meant GE had to deliver an engine for a plane that didn't even exist yet. Competitors at Pratt & Whitney and Rolls-Royce watched closely, convinced GE's gamble would end in disaster. Brian Rowe, the executive who championed the project, described the mood inside GE as tense but determined. He later recalled, "We were betting the company. If it didn't work, we were out of the business." Engineers and executives faced a simple reality: either leap ahead or get left behind. The industry was shifting toward bigger, more efficient twin-engine jets, and the old playbook wouldn't cut it. GE's leadership committed to radical engineering, composite fan blades, record-breaking thrust, and a design philosophy that would upend decades of tradition. The full weight of GE's future rested on a single, unproven idea. For Rowe and his team, there was no turning back. In November 1992, a team of GE engineers gathered around the first full-scale GE90 engine core. Months of design and sleepless nights came down to a few hours of stress testing. The core roared to life, delivering the kind of power the team had only seen on paper. Nothing in commercial aviation had ever pushed this much air through a single core. The successful core test proved that their radical design could survive real-world forces, clearing a major hurdle for the program. Just 4 months later, in March 1993, GE assembled the first complete GE90 engine. The stakes were even higher now. The engine was mounted on a test stand, and technicians monitored every sensor as the turbines spooled up. The numbers were staggering. Initial thrust reached nearly 85,000 pounds. Those present described the sound as a deep, rolling thunder, unlike any engine before it. December 1993 brought the next leap, the GE90's first flight. Engineers bolted the prototype onto the wing of a Boeing 747 testbed and sent it skyward. The engine performed flawlessly, logging hours in the air and handling everything from rapid throttle changes to simulated emergencies. Each test delivered data that would shape the engine's final design, but the pressure was relentless. Every milestone raised the bar, and every success made the next challenge more daunting. By the end of that year, the GE90 had moved from concept to airborne reality. Yet, with each test, new questions surfaced about materials, durability, and long-term reliability. The early results were promising, but the team knew that proving the engine's strength on paper and in test cells was only the beginning. The next phase would demand breakthroughs in materials science and manufacturing, setting the stage for the composite fan blade revolution. Engineers at GE faced a challenge that went beyond scale. They needed a fan blade that could survive forces no metal had ever endured. Traditional titanium, while strong, proved too heavy for the massive 128-inch fan they envisioned. The answer came from an unlikely source: carbon fiber composites, a material known for its strength-to-weight ratio and flexibility under stress. This was not a minor tweak. It meant rethinking how jet engines were built, certified, and maintained. GE partnered with SNECMA of France to form Tefan, a dedicated joint venture tasked with perfecting the manufacturing of these composite blades. The early days were rough. Fewer than 1 in 3 blades passed inspection, with each failure offering new lessons about fiber alignment, resin curing, and the unpredictable ways carbon fiber behaved under load. But when the process worked, the results were undeniable. Composite blades weighed about half as much as their titanium predecessors, yet could flex and absorb impacts that would shatter metal. The scale was staggering. The GE90's fan, at 128 inches, was wider than the fuselage of a Boeing 737. Lighter blades made it possible to spin this giant disc at high speeds without tearing itself apart, enabling the engine to move more air, burn less fuel, and deliver record-breaking thrust. This leap in materials science wasn't just an engineering feat. It redefined what a jet engine could be. The GE90's compressor section became a proving ground for engineering discipline. Early prototypes revealed that complexity bred risk. 10 tightly packed stages drove performance, but also made manufacturing unpredictable and repairs costly. GE's engineers faced a stark choice: simplify or accept a bottleneck that could undermine the engine's promise. In 1998, the team executed a bold redesign, trimming the compressor from 10 to 9 stages and adding a 4th booster stage. This was not a mere tweak. It required rethinking airflow, pressure ratios, and thermal loads across the entire core. The payoff was immediate. Manufacturing yields surged past 90%, turning a chronic production headache into a model of consistency. Validation demanded more than spreadsheets and simulations. Thousands of hours of ground and flight tests followed, each designed to expose the compressor to the harshest conditions it would ever face. Engineers ran the engine at maximum power, cycled it through rapid throttle changes, and subjected it to thermal extremes that would have crippled earlier designs. The data told a clear story. The new core delivered not just higher thrust, but also unmatched durability. These results became GE's ace in the next round of negotiations with Boeing and airlines. Proof that the engine could deliver on its ambitious promises, not just in the lab, but on the runway and in the skies. Boeing's boardroom became a battleground in July 1999. Months of tense negotiations reached a breaking point as Jim McNerney, then president of GE Aircraft Engines, pushed for a deal that would change the future of commercial aviation. Boeing executives weighed their options: stick with the traditional multi-supplier model, or gamble on a single engine for their most ambitious 777s. GE's offer stood out, not just for its technical confidence, but for the financial stakes. GE pledged $100 million in direct support for Boeing's development costs, plus $400 million to complete the GE90-115B, the most powerful engine ever proposed for a passenger jet. The deal locked out Pratt & Whitney and Rolls-Royce, making GE the exclusive engine supplier for the 777-300ER and 777-200LR. Air France became the launch customer, validating Boeing's decision and securing the business case for GE's massive investment. Overnight, the balance of power in the jet engine market shifted. For McNerney and his team, it was the payoff for years of risk and relentless pursuit. More than 2,800 GE90 engines now power the world's long-haul Boeing 777 fleet, logging over 100 million flight hours since entering service. Airlines rely on the engine's dispatch reliability, which consistently exceeds 99.9%, an industry benchmark that has reshaped expectations for twin-engine aircraft on intercontinental routes. The GE90's sheer power and durability allowed airlines to retire older 4-engine jets, streamline maintenance, and unlock new non-stop routes that were once impossible. Yet the engine's enormous size and complexity have drawn criticism in recent years. Its 128-inch fan diameter limits compatibility to the 777, and the cost of maintaining such a large, advanced engine can challenge airline budgets as fuel prices and environmental regulations evolve. Still, the GE90's core innovations, composite fan blades, high bypass ratios, and advanced digital controls, created the foundation for GE's next leap, the GE9X, designed for the Boeing 777X. The lessons of the GE90 continue to drive the search for greater efficiency, lower emissions, and more sustainable flight. Over 2,800 GE90 engines have logged more than 100 million flight hours since the program began in 1990. The GE90 was the first commercial jet engine to use carbon fiber composite fan blades, setting a new benchmark for power and reliability. Its 128-inch fan diameter and 115,000 pounds of thrust made it the most powerful engine of its era, with a dispatch reliability above 99.9%. Yet, some technical details, such as proprietary manufacturing processes, remain undisclosed by GE. Experts agree the GE90's bold engineering and market dominance directly shaped the next generation of engines, including the GE9X. Today, as airlines seek lighter and more sustainable solutions, the GE90's record stands as both a milestone and a reference point. Its legacy demonstrates how a single risk, backed by $1.5 billion in years of innovation, redefined what's possible in commercial aviation.